Okay, first thing we're gonna start talking about this morning is properties associated with the periodic table. So properties on the periodic table. Now, before we get into that, we need to really look at the periodic table. On our periodic table, we have 18 vertical rows. Those rows are called families, okay? Group 1, that's a family, has hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. They are very similar. They react very similar. They react different than group 2 because they're not in the same family. Okay, so we have 18 groups or families, which are vertical rows. We have 7 periods. Okay, 1 through 7. The periods change in properties as you move across the period, whereas a family has very similar properties from top to bottom. There may be one odd member of a family that has different properties, but for the most part, they all react the same. Now, when we talked about electron configurations, remember these two bottom rows actually fit right here, okay, to expand out the periodic table. So we still just have 7 periods. So we have different properties that we can compare to families on the periodic table. The first property is atomic size. An atomic size is the size of a neutral atom. Okay? So, if we draw us a generic periodic table, that looks like a generic periodic table, wouldn't you say? Okay? How do you think atomic size would change with respect to the periodic table? Well, what governs atomic size? The number of protons, neutrons, and electrons, right? Essentially, if we're going to look at just protons and neutrons, they're all located in the nucleus. They're not going to have very much of an effect on atomic size. But when we start adding electrons, it takes up more room, okay? Kind of we can visualize it as a classroom of people. There's probably 40 desks in here, okay? Can we put 40 desks in a smaller room? No. It takes up too much space. Same thing with electrons. We put our electrons together, they start taking up more area, more air, more volume, and they get further and further apart, and they make the molecule or the atom bigger. So, atomic size would increase as you go across a period, and it would increase as you go down a family. Okay? Now, we could say it decreases as we move from right to left, or decreases as we move from bottom to top. It's up to us as how we want to describe what's happening there. So, atomic size, the first property, is the size of a neutral atom, and you agree that things on this side are bigger than things on this side within the same period. Things at the bottom of a family are larger because they have more electrons than things at the top. Okay? The second property is ionic size. And we're going to do this a little bit different than the way the book describes it. Our definition of ionic size is the size of the most common ion or ion. Okay, now an ion is a charged species. Okay, it's an atom that has gained or lost electrons. So generally, if we're looking at metals, metals generally lose electrons to form a positive ion. Okay, that positive ion is called a cation. Okay? Nonmetals gain electrons to form a negative ion called an anion. The process whereby we gain or lose electrons is called ionization. Okay, the loss of an electron. If we're looking at losing electrons, the first electron requires, let's say, 10 joules of energy. How many joules would the second require? More than 10 or less than 10?
More,
Why would it require more?
because the more protons,
You have more protons with respect to the electrons, right? So the electrons are held tighter. So as you go up in removal of electrons, it takes more energy. This ionization is governed by something called ionization energy. Ionization energy is the amount of energy to remove an electron. Okay, so the first ionization energy we're going to call ionization energy 1. Okay? Ionization energy 1 is less than ionization energy 2. Because it takes more to remove the second one. And it's less than ionization energy 3. So, the more electrons we remove, the more energy it takes. Now, on the generic periodic table, okay, our generic periodic table is broken down into what we refer to as the metals and the non-metals. Metals generally want to have a positive charge. Non-metals generally want to have a negative charge. So if we have a positive charge, what happens? We do what? Lose electrons. If we've got a negative charge, what do? We gain electrons, right? So if we gain electrons, we get larger in size. Do you not agree? And if we lose electrons, we get smaller in size. So if we're looking at it in this way, it's going to increase in size in that direction for ionic size, and it's going to increase in size for that direction. So if we're just looking at ionic size, it's going to increase as we go down, and it's increased from left to right. Now, if we're looking at ionization energy, the smaller the atom, the more energy it's going to take, right? So at the top, upper left-hand corner for hydrogen, it's going to take a lot of energy to remove an electron. Okay? So be sure what you're being asked. If we're looking at it in terms of size, it changes in that manner. If we're looking at it in terms of energy amount, it's going to change in a different direction. Okay? It's going to be opposite. It's going to increase the smaller you get. Okay? So there's our first two properties based on the periodic table. We've got another property called electron affinity. Okay, and this is the amount of energy that must be added to a neutral atom to form a -1 ion. Okay? That's electron affinity. Now, we still have our generic periodic table here. Okay, and I'm going to put another one on the other side. Okay, so if we have our generic periodic table, okay, remember we have the stair step here. Metals are on this side. And remember, metals want to form a positive charge. Non-metals are over here, and they want to form a negative charged ion. Which side, or which direction on the periodic table is it going to be easier or take the least amount of energy to add an electron?
Non-metals.
Non-metal, so it's going to decrease in that direction, right? Agree? It's going to decrease. As we move towards the non-metals should be the ideal location where we have a minimum amount of energy. Now what about
The energy decreases?
the energy decreases? So what about the family? What about the family? What about the vertical rows?
Going down to decrease.
Going down and decrease. Why? You're right, but why? Because it's bigger, so it's more area
To play with.
more area to stick something, right? It's like if you go to the grocery store. Okay, have you ever been to the grocery store? You ever been to Rouse's? I noticed this at Rouse's. At Rouse's, you have two types of grocery carts. Okay, you got the traditional full-size grocery cart. Okay, and you fill it up, put a lot of stuff there, and got a little rack on the bottom. Then you have the little dainty grocery cart that will hold a bag of chips, maybe a loaf of bread, and some fruit. Okay? If you're going shopping, and you're really going shopping for groceries, which grocery cart do you want? Why? Because you got more room. Now, do you have to fill it up just because you have it? No. Okay? But if you really want to get some groceries, you want the big one because you've got room to put them. If all that's available is the little one, you're going to have 3 or 4 of them tied together so you've got a basket to hold everything as you move through the grocery store. Okay? So the same thing happens here with electron affinity. If we have room to put electrons, which we do, when we get larger and larger and larger within a family, it's easier to do it, so it decreases the amount of energy required. When we move from left to right towards the nonmetals, it decreases the amount of energy that's required because the nonmetals would rather have a negative charge than they would a positive charge. Okay, another property, electronegativity. Electronegativity is the relative tendency of an atom to pull an electron to itself in a chemical bond. So, in other words, it's a ranking of how tightly the electron is pulled to one of the atoms in the bond. Now, there are 3 types of bonds. 3 types of bonds. There's a covalent bond. In a covalent bond, we have equal sharing of electrons. Okay? So we have a difference in electronegativity between 2 atoms in a bond somewhere between 0 and 0.05. Okay? We have a polar covalent bond, which is unequal sharing of electrons. And we have a difference in electronegativity here, somewhere between 0.05 and 1.25. Now those endpoints for both of these are kind of fluid. It could be a little bit greater than 1.25 to make it polar covalent. Okay? True covalent bonds have a difference of 0. Okay, but those that have just a slight difference are considered covalent. And we have a third type of bond called an ionic bond. In an ionic bond, we have no sharing of electrons. In an ionic bond, one of the atoms strips the electron from the other, so our difference in electronegativity is greater than 1.25. Okay? So we've got three types of bonds. Now, we need to know about our electronegativities. Okay, so we got our generic periodic table again. Okay? Here, this element here is fluorine. It has an electronegativity of 3.98. Okay? As determined by Pauling, on the Pauling scale. Okay? We've got 3.98 here. We have down here with francium 0.7. Okay? How do you think electronegativity changes? It should increase in this direction, right? And it should increase in this direction. Okay? So the largest number on the periodic table, according to Pauling, is 3.98. Okay, the actual Pauling scale of electronegativities originally went from 0 to 4. So 3.98 is pretty close to 4. Okay, you have different elements that have different things. For instance, oxygen, oh gosh, if I remember, oxygen is 3.44 or 3.16. Carbon's 2.55, hydrogen's 2.10. So you got an atom bonded to another atom sharing a pair of electrons. And let's say one of those atoms had an electronegativity of 2.1. The other one had an electronegativity of 2.55. So the difference there would be what? 2.55 minus 2.1 would be 0.45. Okay? So what type of bond would I have? Would I have a covalent bond? No. Would I have an ionic bond? No, I would have a polar covalent because the 0.45 falls between 0.05 and 1.25. Okay? Does that make sense? Okay. Any questions on those four properties associated with the periodic table? Atomic size, ionic size, electronegativity, electron affinity. We're all good on that? Okay.